Good morning, students. Today we'll discuss some characterizations of compactness in terms of convergence of filters. So our first theorem is a topological space X tau is compact if and only if every filter on X has a cluster point. So first of all, let us take X is compact and F is a filter on the set X. Now we prove that this filter F has a cluster point. In order to prove that the filter has a cluster point, let us take a family consisting of all those subsets of X which are of the form of A closure, where A is some member of the filter F. Now, this collection is a collection of closed subsets of X. Now, in order to use the concept of compactness, we will have to prove that this family has finite intersection property. So let us take the members B1, B2, B3 up to Bn belonging to this family. Now, by definition of family B, these members are of the form of closures of some members of filter F. So, there exist A1, A2, A3 up to An belonging to the filter F such that each Bi, that is of the form of closure of Ai. It means B1 is A1 closure, B2 is A2 closure, and so on. Bn is An closure. And therefore, intersection Bi, I varies from 1 to n, that will become intersection of Ai closure. Here, I varies from 1 to n. Now, to show that this intersection is non-empty, we will have to show that intersection Ai closure, where I varies from 1 to n, that is non-empty. Now, because Ai belongs to the filter F and we know that superset will also belong to filter F, so Ai closure also belongs to the filter F, being a superset of Ai. And this is true for every I varying from 1 to n. And therefore, we can say that intersection Ai closure belongs to the filter F. And because we know that phi does not belong to any filter, so this intersection, that is non-empty. So we can say that intersection of Bi, I varies from 1 to n, that is not equal to phi. So this proves that the family B has finite intersection property. Now, because X is compact, so by using the characterization of compactness, we can say that the intersection of members of this family will be non-empty. So intersection of B, where B belonging to the family B, that is non-empty. Now, let us take X belonging to this intersection. So, by definition of intersection, it means X belongs to B for every B belonging to this family. The members of this family are of the form of closures of some members of filter F. So, it means X belongs to A closure for A belonging to the filter F. So, by definition, this proves that X is the cluster point of the filter F. Now we do the converse part. Conversely, we are given that every filter on the set X has a cluster point. And we have to prove that X is compact. In order to prove that X is compact, let us take a family of closed subsets of X having finite intersection property. In order to prove X is compact, we will have to show that this family B has non-empty intersections. So let us define a collection of all those subsets of X which contains the finite intersections of members of family B. Now we claim that this collection is a filter on the set X and this contains the family B. Now first of all we show that family B is contained in this collection F. Now because for A belonging to this family B, A contains intersection AI, I varies from 1 to n. Yet each AI can be taken as A because A contains A, and so on up to n times. So this condition is satisfied for A. So we can say that A belongs to the collection F. A belonging to collection B implies that A belongs to the collection F, and therefore the family B is contained in the collection F. So this proves that this collection F is non-empty. Now next we show that phi does not belong to the collection F. If we take an arbitrary member A belonging to the collection F, then by definition of collection F, A contains intersection AI, I varies from 1 to n, where this AI, they are belonging to the family B. Now because this family B has finite intersection property, so this intersection that is non-empty and A contains this intersection, so A will also be non-empty. So this proves that phi does not belong to the collection F. Now in the next condition, let us take A belongs to the collection F and B is superset of A. Now we are to prove that B also belongs to the collection F. Now A belongs to F, so by definition of F, A contains finite intersections of members of family B. Now we can combine these two. Intersection of AIs is contained in A is contained in B. So we can say that intersection AI, I varies from 1 to n, that is contained in B. It means B contains the finite intersections of members of family B. So we can say that this B belongs to the collection F. Now in the next condition, let us take two members A and B belonging to the collection F. Now because A belongs to the collection F, so by definition A contains finite intersections of members of family B. In the same way, B belongs to the collection F means B contains finite intersections of the members of family B. So from here we can say that A intersection B contains some finite intersections of members of family B. It means A intersection B belongs to collection F. So collection F satisfies all the conditions for being a filter, and therefore we can say that this collection F is a filter on the set X, and also this filter contains the family B. Now we are given in the statement that F has cluster point. Every filter has a cluster point. So this filter F will also have cluster point. Let us take X with a cluster point of this filter. So by definition of cluster point, it means X belongs to B closer for every B belonging to the filter F. Now because this condition is true for every member B of the filter F. Now because this family is contained in B, so in particular this condition is also satisfied for every member of this family. Therefore we can say that X belongs to A closer for every A belonging to the family B. Now because the members of this family are closed, so their closures will be identical to the sets itself, and therefore from here we can say that X belongs to A for every A belonging to this family, and therefore X belongs to the intersection of members of this family. So we have proved intersection of members of family B, that is non-empty. So this proves the set X is compact. Now the next characterization of compactness is a topological space X top is compact if and only if every ultrafilter on the set X is convergent. So let us take X is compact and F is ultrafilter on the set X. We are to prove that this ultrafilter is convergent. Now, because X is compact, so by the above theorem, every filter on the set X will have cluster point. So the filter F will have a cluster point. Let us take that cluster point is X. Now, because the filter F is an ultrafilter, and we already discussed in filters that every ultrafilter converges to each of its cluster points, and therefore here X is a cluster point of filter F, implies that filter F will converge to X. So we have proved that the ultrafilter F is convergent. So this proves one of the parts. Now we do the converse part. In the converse part, we are given every ultrafilter on the set X is convergent, and we are to prove that X is compact. In order to prove X is compact, we claim that every filter on the set X has a cluster point. So let us take a filter F on the set X. Now let us use ultrafilter principle. According to ultrafilter principle, there exists a finer filter F star on the set X which contains F. So by ultrafilter principle, there will exist a finer filter F star which is an ultrafilter. Finer filter means that will contain the filter F. So F star is containing the filter F, and it is an ultrafilter. By given condition, every ultrafilter on X is convergent. So the filter F star that is convergent. So there will exist a point X belonging to set X such that the filter F star converges to X. Now we claim that this X is cluster point of filter F. By definition of cluster point, we are to prove that X belongs to A closure for every A belonging to the filter F. In order to prove that X belongs to A closure, we will have to prove that intersection of every neighborhood of point X with the set A, that should be non-empty. So let us take an arbitrary neighborhood of the point X, and that neighborhood we have taken as W. Now W is neighborhood of point X, and the filter F star converges to X. By definition of convergence of filters, the neighborhood system of the point X will be contained in the filter F star. So W belonging to NX implies that W belongs to filter F star. Now W belongs to F star, A belongs to filter F, F is contained in F star, so A will also belong to F star. Now F star is a filter that is closed under finite intersections. A belongs to F star, W belongs to F star, so their intersection will also belong to the filter F star. And F star is a filter, and filter is non-empty, phi does not belong to any filter, so this intersection that is non-empty. So we have proved that intersection of every neighborhood of the point X with the set A, that is non-empty. So by definition, this proves that X belongs to A closure for every A belonging to the filter F, and this proves that X is cluster point of the filter F, and this proves that X is compact. So this completes one of the characterizations of compactness in terms of filters convergence.